Question 2 then, we start off with looking at forces acting at a distance. We're asked to describe an example of another type of force, not gravitational, acting at a distance. So any forces acting at a distance, we're thinking of non-contact forces, things like friction, air resistance, anything like that will not apply because you need to have contact. So you'll be aware of 3 non-contact forces. One is gravity, you can't mention that, not gravitational. The other 2 you'll have seen are magnetic and electrostatic. So you have to describe an example for 2 marks. So you need to give the example, you need to describe it. So you could, for example, say magnetic force, 1 mark, between the poles of, or 2 poles of magnets. So you could say, for example, there's a repulsion between 2 south poles of 2 different magnets, or you could say a north pole and a south pole attract. Both of those would be sort of describing your situation. Or you could go down the electrostatic route, so you could say that the electrostatic force, 1 mark, acts when, for example, we could have a proton near another proton and they push each other away. So there's a repulsion between 2 positively charged particles. That would be another example. But as long as you've named your force, you get 1 mark, and as long as you describe your situation, you get the second. Now, the second part of this question, we're going to get into a bit of calculation. You can see we have a cliff. Let's grab the whiteboard. There we go. So we've got a cliff, and we have a rock falling, and we're told that the rock has a force of 150 newtons acting on it. That's basically the weight of the rock, isn't it? The force pulling it down. It falls down a cliff of height h, and we are told that the work done by this force is 2,700 joules. We're transferring 2,700 joules of energy to that rock to make it fall faster and faster. So we need to work out first of all what the height of the cliff is going to be. So we're trying to find height. We know energy and we know force, so we're thinking of an equation with height, energy and force. There isn't really one, but we do know an equation not with height, energy and force, but with distance, energy and force. And distance is basically, height is basically a form of distance, so we're going to go with that one. So the equation that you'll have used for this one is work done is equal to force times distance, W equals FD. Sometimes you may have seen it written down as E equals FD, energy is force times distance. Either is fine because work done is exactly the same as energy transferred. Now you're trying to work out the height of the cliff, so in other words you're trying to find out the distance. So if we rearrange this, we need to divide both sides by f. If I divide this side by f, I'll get d. This side will be E over f, so we have d is E over f. Distance is energy divided by the force. So already we've rearranged, that would be 1 mark for that. To put the numbers in will get us another mark, so our energy is 2,700 and our force is 150. Show the numbers in, that will give you 18, exactly 18 in fact. That will work out quite nicely. 18 metres, so 1 mark for the rearranging and 1 mark for substitution and evaluation. Numbers in and getting your answer there. Okay, and of course you get 4 marks if you get the correct answer without your working, but always show your working just in case you mess up shoving the numbers into the calculator. It does happen, even to the best of us. Now, we've got our height of our cliff, which is lovely. Let's see. Moving on to the next question. Let's bring that down a little bit. There we go. Now, interestingly, for this one, it says state. Now, those of you who are familiar with your command words in exams will know that that is a good sign. It means you've got no calculation to do. The number that you're going to give here will require no calculation. It will just be you quoting a number you've already seen. Often it will be written in the question. There's potentially that it might be a number that you've worked out yourself, but you've got no more calculations to do. So, we know all that from just this first word. State the value of the kinetic energy of the rock just before it hits the ground. Well, we go back to the situation. We're transferring 2,700 joules of energy to this thing as it falls. That energy is going into the form of kinetic energy because the thing is going faster. So by the time it reaches the ground, it will have 2,700 joules of kinetic energy. So your answer is just 2,700. All of that energy is converted into kinetic energy. 2,700 joules. We move on. The mass of the rock is 15 kilograms. Calculate the velocity of the rock just before it reaches the bottom of the cliff. So what do we know? We know mass, which is m, and we know the kinetic energy from that last part there. We know the Ke. And we're trying to work out what the velocity is, so we need an equation with m, Ke and v. Well, that's going to be your kinetic energy equation, which if you remember is Ke is equal to half mv squared. Now we're trying to find the velocity, which means going to do some rearranging. I need to get at this v, and we've got a bit of an issue here because there's bump around. So first of all, let's get rid of this half. We can do that by multiplying both sides of the equation by 2. 2Ke will give me mv squared. I've got this m in front of my v, and I've got this squared. I can't really square root this because that would involve square rooting the m as well, which is going to be a mess. Let's just divide both sides by m. We'll end up with 2Ke over m is equal to v squared. And that simply means, of course, that to get v we just need to square root the whole thing. Root of 2Ke over m is equal to v. There we are. So that's obviously one of the more complicated rearrangings. You can bet we've got a mark for just the rearranging at the very least. We've got to work out what v is, so you just put the numbers in. So it's going to be 2 times the kinetic energy, which was 2,700 joules, divided by the mass of 15 kilograms, square root the whole thing. So let's put that in the calculator and see what we get. So I'm going to do 2 times the kinetic energy divided by the mass, and then I'll square root the whole thing so I don't get mixed up. So it'll be 2 times 2,700 divided by 15. There it is, 360. We're going to square root our answer. Might be slightly different keys for you, of course. 18.97 blah, blah, blah. You are at no point going to write that whole number down. It's 18.9 blah 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 blah. That's going to round to 19. Again, 2 significant figures, because the 2 figures we used earlier were to 2 significant figures as well. 19 meters per second for that one. Incidentally, I just mentioned this while we're here on this one. There is another way that you could do it. You could use this equation here, v squared minus u squared equals 2ax, where v is the final velocity, u is the initial velocity, a is the acceleration, and x is the displacement or distance in a particular direction. That would work. You could rearrange that. That will get you your answer as well. Okay, and there's one final part to this question. Let's flip that over. Pages are tricky. So with this one, all we have to do is describe this graph, essentially. We have to describe how the efficiency of the electric motor depends on the mass of the box lifted. So we've got a graph, it goes up, goes down again. And you've got to describe that. It's a 2 marker, so you're not going to go into a huge amount of detail, but we're looking for more than just sort of saying it goes up, because clearly there's more to it than that. So if you're going to describe it in a lot of detail, I guess you would say as the mass of the box increases, the efficiency increases rapidly at first, and then slows down its rate. You could say at around about perhaps 25-30 kilograms, that sort of area. We have our maximum efficiency, and then it decreases slowly after that. It's only 2 marks, so you're not going to have to go into a huge amount of detail, so we're really looking for you to say that the efficiency increases at first, and then for your second mark to say where about the sort of maximum efficiency is going to be. So it's around about 25 to 30 kilograms there. After that, the efficiency, of course, starts to decrease, and that is question 2.